Hey everybody, John again. In the last video we found all the solutions without being restricted to an interval. In this one we are restricted to the interval from 0 to 2 pi, so we're going to have a finite solution set here. But what's different here is the inside of my trig function is not just x. And so I need to work this a little bit differently. And we'll talk about what that looks like. And in the next example, we're actually going to use the same idea that we used in the last example where we found all the solutions to help us figure out which ones are in the interval that we're talking about. So in this problem, first I want to get sine by itself. So I'm going to subtract 1 from both sides. So I have 2 sine of x minus pi over 4 equals 1. And then I'm going to divide by 2. And so we have sine of x minus pi over 4 equals 1/2. So normally, I know that if I plug pi over 6 into sine, I'm going to get 1/2. Also, if I plug in 5 pi over 6, I'm going to get 1/2. And so I want this entire inside to equal pi over 6 or 5 pi over 6. And so what I'm going to do is, just for now, let's replace theta with x minus pi over 4. Just to make this easier to look at, if I let theta equal x minus pi over 4, then I just get sine of theta equals 1/2, which means that theta equals pi over 6, and theta equals 5 pi over 6. Now, knowing where sine of theta equals 1/2 is going to come up a lot today, so just get used to that. But remember, this isn't really what I'm looking for. I'm looking for x. I'm not looking for theta. And so I'm going to set x minus pi over 4 equal to pi over 6. And I also want to set x minus pi over 4 equal to 5 pi over 6. Now, if I add pi over 4 to both sides, x equals, common denominator here is going to be 12. So this is actually 2 pi over 12 plus 3 pi over 12 is pi over 4. So that gives me 5 pi over 12. And then if I add pi over 4 over here, that's going to be 10 pi over 12 plus 3 pi over 12. That's going to give me 13 pi over 12. So far, I know that x equals 5 pi over 12 and 13 pi over 12. But maybe there are more solutions between 0 and 2 pi, because this is only pi over 12. This one's only pi over 12 past pi. So there might be another solution somewhere if I add a period. Okay? Well, the period of sine is 2 pi. So if I add a period to this, I'm going to be past 2 pi, because 2 pi plus 5 pi over 12 is definitely bigger than 2 pi. And so, and definitely if I add 2 pi to this, I'm not going to end up within 0 to 2 pi. So I do have to check to see if there are more solutions if the period has been changed. So this next example is going to show us that. For this one, since the period is still 2 pi, these are the only two solutions that I'm going to find. However, in this next problem, with the 3 inside of cosine, my period is actually 3 times shorter than it was. So that means normally I'd have 2 solutions to this equation, but now I should have around 6, if not more. So let's go through this. Again, I'm going to let theta equal 3x. So I'm really looking for what angle makes cosine equal 1/2. Well, I know that happens at pi over 3, and it happens at 5 pi over 3. So it's in the first quadrant and the fourth quadrant. So pi over 3 above 0 and pi over 3 before 2 pi. So thinking about our unit circle, it's happening here and here. All right, but my period is not 2 pi. It's 2 pi over 3. And so I need to figure out, are there other solutions? So this would normally be all of the solutions to this, right? But we're not looking for theta, we're looking for x. So if I set 3x equal to pi over 3 plus 2n pi, and if I set 3x equal to 5 pi over 3 plus 2n pi, and then I divide both sides of this equation by 3, I get x equals pi over 9 plus 2n pi over 3. And then over here I get x equals 5 pi over 9 plus 2n pi over 3. So now I can just start plugging in values for n, because remember, n is an integer. N is an integer. So I could start with 0. If I start with 0 and I plug 0 in here, then I'm going to get a value of pi over 9. So x equals pi over 9. Now I could try to maybe even plug in like a -1 here for n, but 2 pi over 3 is 6 pi over 9, so this would come out negative. And remember, we're starting at 0 and going to 2 pi. So the negative wouldn't work. So I'm going to plug 0 into here. And if I plug 0 into here, I get 5 pi over 9. So we're collecting a set of numbers. So let's plug in 1 for n. If I plug in 1 for n, my first equation is pi over 9 plus 2 pi over 3, which I'm actually going to write as, instead of writing 2 pi over 3, I'm going to write 6 pi over 9. And 6 pi over 9 plus pi over 9 is 7 pi over 9. Is that between 0 and 2 pi? Yes, it's actually less than pi. So we're still less than pi at this point. And we have 3 solutions. Let's plug n equals 1 into this one. We have 5 pi over 9 plus that 2 pi over 3, which is 6 pi over 9. And that gives me 11 pi over 9, which is slightly bigger than pi. Let's plug. So this was n equals 1. This was n equals 0, or these two. We tried -1, it didn't work. So n equals 2. X equals pi over 9 plus 4 pi over 3. 4 pi over 3 is better known as 12 pi over 9. 12 pi over 9 plus pi over 9 is 13 pi over 9. 13 pi over 9 is still less than 2 pi. Let's try it over here. X equals 5 pi over 9 plus 12 pi over 9. That's that 4 pi over 3 again. And that gives me 17 pi over 9. 17 pi over 9 is pi over 9 short of 2 pi. So that is still smaller than 2 pi. And my guess is, I'm ending the brackets here because my guess is if I try to make n equals 3, then this isn't going to work, because this is now going to be, it's going to be 6 pi over 3. 6 pi over 3 is going to give me 18 pi over 9, which is already 2 pi. And so if I add to that, I'm only going to be bigger than 2 pi. So here's my solution set for this one. There are 6 solutions, which is what we had figured, because our period is 3 times shorter than it was, and we would normally have 2. So times 3 gives me 6 solutions. All right, I'll see you in the next video.